Welcome back, Focus learners. Let's just jump right into it. Today's explainer takes us straight into the absolute heart of modern invention, drawing from Practical Electronics for Inventors. Specifically, we're unpacking a massive, incredibly dense chunk of knowledge right from the core of the text, pages 250 through 450 to be exact. Consider this for a second. The device you're using right now has billions of microscopic switches firing millions of times a second. Today, we're going to decode the language of electronics, moving from basic, raw building blocks all the way to the complex semiconductors that make our modern world tick. Grab your mental toolkits because we are diving in.
When you picture a naked circuit board, what do you actually see? It usually just looks like a chaotic jumble of plastic, little metal wires, and colorful blobs. It's incredibly intimidating, isn't it? How does that physical mess turn into the smart devices we rely on literally every single day? Well, the secret is that it's not chaos at all. It is a highly structured, perfectly logical system. We're going to learn how to read that chaos and translate it into a language that actually makes sense.
When you first encounter a standard schematic chart, you're immediately hit by the sheer visual density of it all. It's like the matrix of electronics. You've got symbols for everything from basic batteries up to depletion mode MOSFETs. And if that makes you feel completely overwhelmed, trust me, you are not alone. It is a lot, but here's the good news. This is just a language. And like any language, you don't learn it all at once. You learn the alphabet, then the words, then the sentences. I promise you, we are going to systematically break this language down together, piece by piece.
Okay, so to decode this language, let's step out of the abstract and get into the physical world. At the micro level, we need to decipher the literal components sitting right there on your workbench. These are the most ubiquitous pieces in any electronic device, and the very first thing you need to know is how to read what they're trying to tell you.
Take your standard everyday resistor. It doesn't have its value printed out in nice, easy-to-read numbers. Instead, it wears this mysterious set of colored stripes. Now, it looks almost decorative, but those stripes are actually a highly efficient, secret mathematical code printed right onto the component. It allows engineers and inventors to quickly identify properties without needing a magnifying glass to read tiny text.
So, how does the code work? It's actually pretty simple. In a common 4-band resistor, the first 2 bands represent significant figures. Black is 0, brown is 1, red is 2, orange is 3, and so on. The 3rd band? That's your decimal multiplier. Basically, how many zeros to tack on to the end. So a resistor with red, black, and orange bands translates to a 2, a 0, and then 3 more zeros. That's 20,000 ohms, or 20 kiloohms. The final band just tells you the tolerance. Ultimately, memorizing this simple color rainbow vastly improves the speed of your workflow. It becomes so practical for any hobbyist building a prototype to just glance at a bin of parts and know exactly what they're holding.
And you know, this coded language extends to capacitors too. If resistors use a color rainbow, surface mount and ceramic disc capacitors use an even more cryptic set of microscopic numbers. You'll see these little packages with a label that just says something like 104 or 47p. At first glance, it means absolutely nothing. But just like resistors, these tiny labels hold massive engineering value if you know how to crack the code.
Think about it. When a part is literally the size of a grain of sand, printing 100,000 picofarads simply isn't an option. That's why the 3-digit code is brilliant. It works just like the resistor bands. First 2 digits are the significant figures, 3rd digit is the multiplier. A label of 14 means a 1, a 0, and 4 more zeros. Boom, 100,000 picofarads. If you have a tiny value under 100, the letter R is often swapped in for a decimal point, making 22R exactly 22.0. And letters at the end, like K or M, those are just standard tolerance codes. Grasping these fundamentals totally empowers you to pick up any tiny capacitor and instantly know its exact value.
So, as we transition from these individual components to how they actually interact with each other, there's this great direct quote from the authors of our source text regarding the math behind complex circuits. They write, "This section is designed to scare you." I absolutely love that honesty. They readily admit that if you try to use raw Kirchhoff's laws to model every single parameter of a massive, nonlinear circuit, the equations become a total nightmare. So, it is completely normal to feel a bit intimidated by the dense math of circuit modeling. But don't worry, because the authors offer this incredibly powerful alternative trick to bypass those nasty equations, and it's called Thevenin's theorem. Instead of calculating the entire complex network all at once, you simplify it. Step 1, remove your load. Step 2, short your voltage source. Step 3, calculate the equivalent resistance of that isolated section. And step 4, recombine it into an incredibly simplified subcircuit that behaves the exact same way. It is a brilliant step-by-step recipe that takes a chaotic web of resistors and batteries and turns it into one simple voltage source and one simple resistor. Practically speaking, this trick is the difference between spending hours doing grueling calculus versus 5 minutes of basic algebra.
But even with slick math tricks like Thevenin's theorem, a core problem remains. Electronics are invisible. You can't see an electron moving. You certainly can't touch voltage. So how on earth can we visualize abstract concepts like current flow or how an inductor resists a change in that flow? We need a mental model, something that bridges the gap between abstract math and actual physical reality.
Enter the water analogy. Honestly, this is an absolute game changer for your mental toolkit. It makes invisible electricity tactile and mechanical. Think of current as water flow, voltage as pressure, and a resistor is just a pinch in the pipe. An inductor? Picture that as a heavy mechanical water turbine or a flywheel inside the pipe. It takes time to get spinning, so it resists any sudden changes in the water's flow. It's such a beautiful way to understand complex invisible forces. Just keep in mind, unlike real plumbing, if your electrical circuit springs a leak, you're dealing with sparks, not puddles.
Now, this water analogy applies so perfectly to arguably the most important component in human history, the transistor. You can look at the dense mathematical schematic of an NPN bipolar transistor, but then compare it to its exact mechanical equivalent, a complex water valve. The parallel is wild. A tiny physical movement in that mechanical water valve directly mimics how a tiny electrical input current can physically open a gate to control a massive, roaring output current.
Let's actually lock this in by mapping the specific parts. In our transistor, we have 3 pins: the base, the collector, and the emitter. In our water analogy, the base is that small control tube on the side. A tiny flow of water comes in here, pushing against a spring-loaded lever. The collector is the main high-pressure water source coming from the top. When the small base flow pushes that lever, it pulls open the massive gate for the collector. Finally, the emitter is the drain at the bottom, which is the combined roaring output flow of both the base and the collector. A small signal controlling a massive flow, that is the very essence of amplification.
And that incredible ability to amplify, that brings us to the true powerhouse of this explainer, and the core of modern invention, the semiconductor. The transistor we just talked about, along with pretty much every smart device today, is built from semiconductive materials like silicon. They're the fundamental, highly complex building blocks that allow us to process information, switch massive currents, and literally light up the screens we stare at all day.
The variety out there is just staggering. We're talking everything from the simplest one-way valves like diodes to LEDs, up to discrete transistors, and all the way to incredibly dense, complex microchips. Even solar cells that turn light into electricity. All of these vastly different devices stem from this exact same exciting branch of material science. By mastering the basic physics of a p-n junction, doping silicon so it has either an excess or a deficit of electrons, you gain almost godlike control over electrical current. That manipulation is what unlocks the entire family tree of modern tech.
But of course, as tech has evolved, so have the semiconductors themselves. It's really vital to draw a clear line between older technologies and modern powerhouses. Earlier, we used the water analogy for bipolar transistors. Those are current-driven devices, meaning you need a physical flow of current into the base to open the valve. But modern microelectronics? They are completely dominated by MOSFETs, specifically enhancement-type MOSFETs. These are voltage-driven. You don't need a steady flow of current to keep them open. You just apply a voltage to the gate, and it creates an electric field that changes the conductivity of the underlying channel. Why does this matter? Because a device that draws almost zero steady current is the exact reason your smartphone battery can last all day instead of 10 minutes.
Now, I know the engineering formulas for these enhancement-type MOSFETs can look, well, pretty intense. You're calculating drain currents differently depending on whether the transistor is operating in the ohmic region, where it acts like a variable resistor, or the active region, where the current is completely steady regardless of voltage changes. You're dealing with threshold voltages, transconductance, and deep construction parameters. But think about it. Because you've built the mental models of current, resistance, and amplification, you now possess the foundational tools to actually decode this math. It's no longer just a wall of scary numbers. It's the precise, step-by-step recipe for building a microchip.
Which honestly perfectly summarizes the core philosophy of our source text. All of this dense theory we've covered, the color codes, the Thevenin simplifications, the water analogies, the deep semiconductor physics, it's not meant to just be memorized for some test. Ultimately, it is a toolkit. As the authors state, inventors possess the technical know-how, but they combine it with intuition and creativity to turn their ideas into real-life gadgets. The theory is simply the fuel for your unique creativity.
So we've taken that chaotic matrix of raw components and decoded it. You now possess the visual language, the mechanical mental models, and the mathematical toolkit to bend invisible electrical forces entirely to your will. The tools are sitting right there on the workbench, waiting. The only question left is, what will you bring to life next? Thanks for exploring this massive topic with me, and I'll catch you on the next one.